In my previous video about particle physics, I briefly mentioned the four fundamental forces and didn't explain them. Commonly referred to as the force carriers, gauge bosons are what elementary particles use to interact with each other in different ways. These ways make up 3 of the 4 forces. As far as we know, fundamental forces cannot be described as any simpler combinations of particle interactions. That's why they're called fundamental. In other words, any force you can think of can be described as either a fundamental force or a combination of fundamental forces. This video is going to focus on one of the 4 fundamental forces, strong interaction.
Strong interaction is the strongest of the 4 interactions, 137 times stronger than its runner-up, electromagnetism. Before I get into it, I'll explain what a hadron particle is. Hadron particles are composite particles made of quarks. For example, a proton, which is composed of 2 up quarks and a down quark. Strong interaction is the reason why protons in the nucleus of the atom, who should repel each other because they're both positive, don't separate. This specific case has a name, the nuclear force. But on an even smaller and simpler scale, strong interaction is actually the force responsible for holding quarks together to form hadrons. For example, the reason why 2 up quarks and a down quark are partnered up to make a proton is because of strong interaction. Gluons are the bosons which are associated with strong interaction. So how does strong interaction really logically work? Through this thing called color charge. There are 3 colors in this concept called color charge: red, green, and blue. Note that sometimes the 3 colors are red, yellow, and blue, but it's more common that red, green, and blue are used. These are not the actual color of the particles. We choose color because it's a way to simply represent what's really going on. Let's say we have a green quark and a red quark, and they're going to couple together to form a hadron. The red quark, let's call it quark A, can send out a red anti-green gluon. By sending out red, it gets rid of its red color. By sending out anti-green, it turns green. To understand this logic, think in numbers. If you subtract -1, you're really just adding 1. So if you send out an anti-green, you're adding green. This gluon goes over to quark B, which is originally green, but it receives an anti-green from the gluon, which cancels out with its green color, and it receives red from the gluon, which turns it red. Our 2 quarks just switched colors, and they keep switching and interacting like this. We can do this with any 2 of the 3 colors. The colors are attracted to each other, similarly to the way negative charges are attracted to positive charges, except there's 3. Let's say we have a yellow quark X and a red quark Y. Quark X sends out a yellow anti-red gluon, getting rid of its yellow color, and turns itself red. Quark Y receives yellow anti-red gluon, turning yellow and losing red. Basically, quark 1 will emit a gluon with their original color and the anti-color of quark 2. This exchange process continues. It's called color changing. This process isn't necessarily between only 2 quarks. Actually, usually it's not. In the simple proton, it's between 3. That's the basic working of the strong force.